What is an eigenvector? An eigenvector is a non-zero vector whose direction remains unchanged when a linear transformation is applied to it. It may only be stretched, shrunk, and reversed. The amount of this change is determined by a number called eigenvalue. In other words, if a matrix A acts on eigenvalue x, the result is the sum of vector multiplied by a scalar of lambda that expressed by ax equal to lambda x.
So, we continue with diagonalization. So, what is the diagonalization? Diagonalization is a process to convert the square matrix A into diagonal matrix D using invertible matrix P, which is A equal to PD P inverse. Okay, why we have to diagonalize matrix? This is because it's much easier to work with, especially when calculating the power of matrix. A the power of n equal to P D the power of n P inverse, instead of multiply by itself repeatedly. So for the condition of matrix A is diagonalization if it's linearly independent for eigenvector. For n multiply n matrix, we need linearly independent eigenvector.
The process begins by finding the eigenvalues of the matrix using the characteristic equation determining A minus lambda I equal to 0. Next, the corresponding eigenvectors are obtained by solving A minus lambda I x equal to 0. The linearly independent eigenvectors are then arranged to form matrix P, while the eigenvalues are placed along the diagonal of matrix D. Finally, the diagonalization is verified using the relation A equals to PDP inverse. Given that matrix A, and the equations are show that the eigenvalue of A are 1, -1, and 3. So we have to use these equations where lambda multiplied by identity matrix minus matrix A and equal to 0. So here lambda multiplied by identity matrix 3 by 3 minus of matrix A, and we can get this type of matrix. Okay, to find lambda, we can use cofactor method on the first column. Since it's easier, it has to be 0 on it. So we can see that lambda minus 1 multiplied by the matrix for closing first column and first row. So we can get this type of equations, and finding this determinant, we can get these equations, and by expanding and factorize the equation on the right hand, we can get lambda minus 1, lambda plus 1, lambda equal to 3. And so we can conclude that lambda equal to 1, equal to -1, and equal to 3. Okay, next for B, we have to find the basis for eigenspace for lambda equal to 3. Okay, we have to insert the 3 value in this equation and argument it with 0 since we see that equal to 0. So for having this matrix, we have to find the low echelon matrix for this matrix. So we can get this one. By this matrix, we can say that A plus 3 over 2B minus 1 over 2C equal to 0, B minus C equal to 0. And we have to list down all the variables, which is A, B, and C. First, since we don't know that what the value of C, we can see that C equal to T as T element to any real number. And as you guys can see, B and A have C on it. So we have to sub C equal to 3 into A and B. So A equal to negative P, B equal to P, C equal to P. Here, like this. So remember, for this question, it needs a basis of eigenspace. So we need of curly bracket for the answer. So for the answer are within 1, 1 and 1. So for the C questions, matrix A is diagonalizable. So yes, A are diagonalizable as lambda has 3 different values.
Okay, for the next question, we need to focus for example for matrix A. We need to find all the engine values of A. First, we apply the formula lambda multiplied with identity minus A equal to 0. Now we have lambda multiplied with identity. So we need to minus with A. So after that, we get the this. After this, we need to find the determinant using first row. Using formula first row. After we apply the determinant, we solve the determinant, you can get the lambda equal to 1, negative 1, and negative 1. So for the next question B, find the basis of eigenspace corresponding to each eigenvalues of A. When lambda equal to 2, sub a matrix in A which have a lambda here. So after we sub it, we need to change this matrix to augmented matrix. For the augmented matrix, we need to find the row echelon matrix. We need to solve all this and also solving. We need to find row echelon matrix. After we apply the solve. Next, we list all the variable x, y, z for row echelon matrix. So we get 2x plus y minus 3z equal to 0 and y equal to 0. And we need to find each value for x, y, z. Z equal to t and t element to r. Y equal to 0 and x equal to 3t. And we get x, y, z 3t, 0t. And we separate the t and we get the answer 3, 0 and 1. And basis for the eigenspace for lambda 2 is curly bracket 3, 0, 1. And next, for lambda minus 1, same like this question, we start in this lambda equal to 1 and negative 1 to A, and we get this. And we have changed to augmented matrix, and we solve the solution until we get the row echelon matrix. After we get the row echelon matrix, we need to list the variable x, y, z, which is x equal to 0, y equal to 0, and z equal to s. S is elementary real number, and we list the s 0, 0 and 1. And the basis of eigenvalues is curly bracket 0, 0, 1. Okay, for the question C, is a diagonalizable if a reason for your answer. Given lambda equal to 1, algebraic multiplicity have 2 for lambda equal to 1 to negative 1, and geometric multiplicity is 1. For lambda equal to 2, algebraic multiplicity have 1, and same as me, geometric multiplicity have 1 too. And you can conclude that from this table, it is not diagonalizable as m not equal to gm.
question 3a, we are asked to find all the eigenvalues of matrix C. First, we find the characteristic equation by calculating the determinant of lambda I minus C and set it equal to 0. After expanding and simplifying the determinant, we obtain the characteristic equation. Lambda minus 1, lambda minus 2, lambda minus 3 equals to 0. Therefore, the eigenvalues of matrix C are 1, 2, and 3. These eigenvalues will be used in the following questions. Next, for question 3b, we need to find the basis for eigenspace corresponding to the largest eigenvalue. From question A, the largest eigenvalue is lambda equals to 3. We substitute lambda equals to 3 into C minus lambda I, then perform row reduction until we obtain the reduced row echelon form. From reduced echelon matrix, we obtain the equation x plus z equals to 0 and y minus 1 over 2 equals to 0. And then we can let z equal to t, where t is any real number. Then we substitute and we can get x equal to negative t and y equals to 1 over 2t. Therefore, the eigenvector can be written as t multiplied by the vector negative 1, 1 over 2 and 1. Hence, the basis for eigenspace corresponding to the largest eigenvalue is negative 1, 1 over 2 and 1. And don't forget to use curly bracket. Finally, for question 3c, we are asked whether matrix C is diagonalizable and we need to give a reason. Since the eigenvalues are 1, 2 and 3, all of them are distinct. A matrix with distinct eigenvalues is diagonalizable. Therefore, we conclude that matrix C is diagonalizable because all of its eigenvalues are distinct.
Next, question 4a. Find the eigenvalues of matrix A. So first, we form the characteristic equation by finding determinant lambda I minus A equals to 0. We subtract matrix A from the identity matrix multiplied by A, resulting in a new matrix. Next, we calculate the determinant using cofactor expansion. After simplifying, we obtain lambda minus 3, lambda minus 1, lambda minus 3 equals to 0. Therefore, the eigenvalues are lambda equals to 1, 3 and 3. So, the matrix has one eigenvalue equal to 1 and a repeated eigenvalue equal to 3 with multiplicity 2. Next, for question 4b, find a basis for the eigenspace corresponding to the largest eigenvalue for matrix A. So, we find the eigenvector for the eigenvalue lambda equals to 3 by solving the equation A equals to 3ix equals to 0. After performing row operations and reducing the matrix to row echelon form, we obtain the equations A equals to 1 over 2c, B equals to 0, and we let the c equals to t, where t is any real number. Therefore, A, B, C equals to t, 1 over 2, 0 and 1. Hence, the basis for the eigenspace corresponding to lambda equals to 3 is 1 over 2, 0 and 1. For question C, is A invertible? Give a reason. So, for question C, matrix A is invertible because all of its eigenvalues are non-zero, which are 1, 3 and 3. Therefore, the determinant of A is the product of its eigenvalues. Determinant A, 1 multiplied by 3 and multiplied by 3. So we get 9 not equals to 0. Since the determinant is not 0, A is invertible. For question B, is A is diagonalizable? Explain your answer. So, based on the table, we can conclude that A is not diagonalizable because geometric multiplicity is not equal to algebraic multiplicity for lambda equals to 3.
In conclusion, this video explained concept of eigenvalues and diagonalization. We demonstrated how to find the eigenvalues and eigenvectors of a matrix, construct matrices P and D, and verify the relation of A equal to P, D, P inverse. Through this process, we showed how diagonalization simplifies matrix operation and helps in understanding linear transformation.